So we've already introduced the dark matter problem, namely that there's just way more matter based on our rotation curves for the galaxies than can be accounted for by our detection methods. So the rotation rate compared to distance, as we go further out, we would expect the rotation rate to fall off, but it stays relatively constant. So here's the outer stars in the galaxy, and they're just going far too fast based on what we can determine is inside to produce gravity to enable them to go that fast. In fact, most galaxies measure to be 10 times more mass than we can account for with regular matter. So that's a huge problem. The mass of all the stars, the dust and gas, and everything else is way too small for the velocities measured. Moreover, there's hot gas. Hot gas is fast-moving gas that does not escape. If the gas is real hot, it means it's moving real quickly, and it's held by the gravitational tug of the galaxy. So the galaxy gravity is actually very huge. This is true for our galaxy and other galaxies we measure as well. So this is based mainly on orbital measurements, and it's such a big problem, and it's got such importance that it would be good to have another independent method of determining this unseen matter. And we do have that, which is gravitational lensing. But let's look at some more ways in which we can discern this extra matter that we can't see. So how do we determine how much dark matter there is in a spiral galaxy? As already mentioned, the size and mass of the galaxies are actually 10 times the size of the visible counterparts. And the way we can determine this is first bring up a model here of the luminous matter of the galaxy, and then the very much extended dark matter halo, way beyond the globular cluster halo in this case. So to determine the amount of dark matter, we need to figure out how much regular matter is. It's the regular matter that produces the luminosity of the galaxy, the stars primarily. So greater mass to light means more dark matter. So we use the actual luminosity to estimate the mass of the stars, the regular matter. And then we can take measurements of the hydrogen clouds, the 21 centimeter line produced by hydrogen, and determine their Doppler shifts, which is going to give us the velocities to get the actual mass of the galaxy. So here's the galaxy rotating around. The gas that's moving toward us, the 21 centimeter line is blue shifted. The part that's moving away, 21 centimeter line is red shifted. We can get the velocities and therefore the amount of mass required to produce those velocities. The result of this is that we see that the spirals are 90% dark matter, matter that's unaccounted for, and only 10% matter that produces luminosity, the stars. We can get similar and corroborating data from elliptical galaxies and galaxy clusters. But let's consider clusters of galaxies that are interacting with each other. It's yet another method. So here's the basic model. We have cluster 1 and cluster 2. They're approaching each other. They start colliding. And as they collide, the gas, the actual regular baryonic matter, the protons, the neutrons, interact with each other. They collide with each other. The dark matter that's in the original cluster moves right through each other. So here's the dark matter from the second cluster, and the first cluster is over here. But the gas itself has collided and heats up. So we're starting to light up the gas that has actually collided, and the dark matter passes right on through. So that's the basic idea, how we can actually measure dark matter in a galaxy cluster. Let's take a look at an actual example. An example, here it is. We have a cluster, two clusters coming at each other. Here we have a larger cluster and a smaller cluster. The smaller cluster over here is moved from the left on through to the right. The larger cluster has moved from the right on through to the left. And just like we discussed, this region here is X-ray emission because the gas has actually interacted and been stripped out of the galaxy clusters and is lit up and producing X-rays. Very hot gas. So that's really an incredible opportunity to, on a very large scale, with galaxy clusters interacting with each other, passing through each other, and seeing the evidence of the dark matter in those galaxy clusters. I mentioned we needed an independent method of validating all this dark matter, and that method is gravitational lensing. This is quite amazing. We've learned that mass distorts space. It bends space. It bends the path of photons traveling through that space. Because of that, a background galaxy in this image is actually revealed in all these different images. These are distorted images of the same galaxy that exist behind this cluster of galaxies. And the reason we see multiple images of them is because the light from the galaxy is bent around this cluster in rather complex ways to give us multiple images. In the same way that a lens bends light to bring to focus an image on your retina. Well, that's very orderly, that process. This is similar, but the bending of the light enables astronomers to view the galaxy that's back there, but not necessarily in a very, high fidelity manner, so to speak. So the massive objects, like a cluster, in this case, can act as a gravitational lens. And the amount of bending that takes place is based on how much mass the lens consists of. The more mass, the more bending there is. Now, the nature of the distorted images that we're seeing here can be analyzed, and the amount of mass required for that determined. So Einstein's relativity tells us just how much mass is required for the particular distortion seen, and that gives us a measure of the dark matter that has nothing to do with orbital velocities or gas speeds or X-ray temperatures from colliding gas from galaxy clusters. But nevertheless, the dark matter determined by this method is consistent with those other methods, and it's a lot. So let me just show you a graphic to make this clear. In this diagram, we see here from Earth, we got a foreground galaxy cluster and a real galaxy in the background. And light could go essentially straight through. Down here, that's the galaxy image we would see. We may or may not see it in reality because the foreground galaxy may be obscuring the view. Light going this way would be bent around, and the way it comes into the direction it hits Earth, projected backward, is where we see the image of the galaxy. Likewise, light coming around this way, we see it coming from this direction, we see the views like that. So that's how a gravitational lens works. Sometimes you get multiple images of a background object, but generally they're not lined up so perfectly. So we get instead, more often, a single distorted image. Here's a case in point of single distorted images of galaxies that are in the background. Okay, so the big question is, what is dark matter? And the fact is, we don't know. Some dark matter is ordinary baryonic matter, regular matter that we're used to. But that would include things like brown dwarfs and black holes and planets, dust and gas that isn't shining. Anything that doesn't shine that's made of ordinary matter is dark, but that doesn't produce nearly enough mass to account for the light bending we see and the orbital velocities we see in galaxies. So we've already addressed this, so I'll go through this quickly, but there's these potentially large objects like brown dwarfs, machos, massive compact halo objects that if they pass across a star like this, then the bending of light of that star can actually enhance the amount of light coming from that star, and we would see that accentuated light. Now we can actually make measurements like this. Here's a case in point where one of these was discovered before, during, and after. You see the brightening of the star as the macho passes in front. But again, this doesn't produce nearly enough. If you do the statistical analysis, With the measurements that are taken, we discover that there's not nearly enough of these type of things out there to account for the vast majority of the matter that needs to be there that's acting gravitationally. So we need to look elsewhere. Some, in fact most, of the matter must in fact be extraordinary, not ordinary. Well, what about neutrinos? Something I've thought about for some years and have been a little skeptical as to whether or not that's been adequately accounted for, because neutrinos are not ordinary. They don't interact with matter very well at all, and it's been determined that they actually do have a little bit of mass. Moreover, they are comparable to the number of photons in the universe, so there's a lot of neutrinos. However, it has been determined that the neutrinos don't, at the upper end of their mass limit, the neutrinos don't account for nearly enough mass to answer the question of the dark matter. So WIMPs. WIMPs stands for weakly interacting massive particles. Things like neutrinos. There are other particles like this that are theoretical, and also ones that are where the theory is starting to be validated through measurements, and they hold promise. So I have a hunch that in the next decade that astronomers are going to actually figure out what the dark matter is, at least most of it. I wouldn't put any big bets on it, but there's a good chance that these weakly interacting but massive particles may actually hold the key to the dark matter. Not so many years ago, in the early 1900s, nobody knew for sure whether the spiral nebula that we're seeing out there were inside or outside of our galaxy. Were they galaxies in their own right, or were they just nebula contained inside our own galaxy? Well, there was a fierce debate going on regarding this for many years. The data just wasn't strong enough to point one way or the other. And of course, this is really important. I mean, it's a huge question in cosmology, because it's just, if the one galaxy is the whole universe, that's really important to know. Or is the universe much bigger, containing many galaxies like our own? Well, then in 1917, the Mount Wilson 100-inch telescope opened its eyes to the sky for the first time, and Edwin Hubble was offered the job at the observatory, but instead he turned it down, and he volunteered for World War I. He was a successful leader, survived the 2 years, and that's a good thing, because he came back in 1919 and took the job and set his sights on Andromeda, the spiral nebula that's observable with the naked eye. He began to actually, just barely, detect pulsating stars, variable stars. He soon came to realize that these were actually Cepheid variables that he was observing. And by comparing the apparent magnitude, how bright they looked, with the period luminosity relation to get the intrinsic luminosity, he showed that those Cepheids in Andromeda were far, far beyond the extent of the Milky Way galaxy. So in one fell swoop, with this very robust data, Edwin Hubble put to rest the debate about whether the spiral nebula were inside or outside the galaxy. And the universe, as we know it, radically increased in size. And of course, that changed our view of the universe forever. In discovering the galaxies, Edwin Hubble secured his place in the history of astronomy. Nevertheless, he wasn't satisfied with that. So after discovering the galaxies, he proceeded to measure the distances to many of these galaxies. And he discovered that, in general, their light was being redshifted. So we noticed the redshifting of light coming from the galaxies. So here is, for instance, an absorption line spectrum for our sun. And you notice here's the similar lines redshifted. This particular amount of shift here corresponds to a velocity, a recession velocity, the Doppler effect, of 7% the speed of light, and also corresponding to a distance of 1 billion light years away. This is not the data that Hubble had, but it makes clear the point. So in 1929, Hubble announced his law, and it goes like this, that the more distant the galaxy, the greater the redshift, thus the faster it moves away from us. That is quite tremendous. In equation form, z, the redshift, is the recession velocity divided by the speed of light. So the amount of redshift is based on how much recession velocity you have, and the recession velocity is based on how far away the galaxy is. Well, just a few years after Albert Einstein had produced his equations of general relativity, which actually implied an expanding universe, which, by the way, Einstein didn't like at all. He wanted an infinite static universe. Nevertheless, this empirical discovery proved that Einstein was right all along. So this had a profound impact on the astronomical community and really stirred things up and propelled astronomy forward tremendously from this particular discovery. This discovery by Edwin Hubble produced what's known as the Hubble law, or the Hubble relation, where the galaxies are receding away from us in a very special way. In fact, the more distant the galaxy, the greater the redshift, thus the faster it recedes. So as distance increases, we notice that the velocity increases as well. So this is the data that Hubble had, where it was able to statistically fit a line to this. So we measured 40 galaxies, producing the relationship between recession velocity and distance based on the redshift, where the redshift is recession velocity divided by the speed of light. The ratio of the recession velocity to the speed of light, it's generally a small fraction. Unless the object is moving so fast it's nearly the speed of light, then it could approach 1. But then it becomes relativistic and things get a little more complicated. In any case, the slope of this line is change in y over change in x. In this case, the change in velocity over the change in distance. Now don't tune me out. This is slope. You've all had slope in algebra. In any case, that slope has a particular physical significance. Velocity over distance. Well, distance over velocity is time. So this slope is actually inverse time, the inverse of time. And it's also known as the Hubble constant and symbolized h naught, h0. That's the Hubble constant. And although you'll see different numbers for the most current value of the Hubble constant, it's around 70 kilometers per second per megaparsec. This unit is actually pretty important. It just says that for every megaparsec of distance, the recession velocity is 70 kilometers per second. 70 kilometers per second, think of that as maybe 40 miles an hour. So that might have been wrong. But in any case, whatever that translates into in miles per second or miles per hour, I can't remember what I said now. In any case, this velocity is based on a parsec. So if you double, if you're 2 megaparsecs distant, that's where the galaxy is, it's receding at 140 kilometers per second. So that's how that Hubble constant can be interpreted. And phenomenally, this enables us to get the distance by just taking the redshift of a galaxy, measuring the redshift, which is a direct indication of the velocity, divided by this Hubble relation, this Hubble constant, and that's the distance to the galaxy. A very powerful tool in astronomy, used very significantly right up to the present time, and the correct value for the Hubble constant is a very important thing that we're always trying to fine-tune. What Hubble did for us was no small thing. He empirically measured the reality of an expanding universe. And the farther away a galaxy is, the greater its recession velocity. That's what the Hubble relation is all about. And here's a sequence of images to show how that works. So we have ionized calcium, these blue lines. In a galaxy that's fairly near to us, the recession velocity isn't that great. The redshift is just a little bit. But as we go further away, we have a greater recession velocity, and there's those lines, see them there, and they're shifted more. Further away yet, the recession velocity is greater, and greater yet, and further away and greater yet, so that the recession velocity is related to the distance that the galaxy is from us. So that's can be measured directly, and it has been many times So it's clear evidence that the universe is in a state of expansion, validating Einstein's original equations. Now, I already discussed briefly Einstein's attitude about this. He really didn't like it at all. In fact, he put in a fudge factor known as the cosmological constant, which turns out to have come back in modern times, but for other reasons. Einstein had this constant that was kind of a repulsive force for gravity to keep the universe static, because he wanted an infinite static universe. That was the paradigm at the time. But he retracted it, confessing that it was the biggest blunder of his career. So a good scientist will do that in the face of evidence. Way to go, Einstein. Well, the expansion away from us has nothing to do with us being in the center. So to try and show you that, here we have the point of view of a galaxy, second to left. There it is. So if you saw that, let's do that again. Notice the other galaxies receding away from that one, and the galaxies that are closer are receding slower, and the ones that are further away are receding faster. But we could have as our point of view the center galaxy here, and if that's the case, then all the other galaxies are receding away from us, with the nearby galaxies being slower and the further away galaxies being faster. So this is the condition for a general expansion of the universe. The same effect would be seen from any galaxy. There's no preferred point of view in this general expansion.